Okay, so this is our third asynchronous little meeting here about statistics. Um, in this one, we're going to kind of do a bit of a dive into how to explore and compare data and some of the numerical calculation that goes into this. So last time around, we were doing descriptive statistics, oftentimes using pictures, things like that. Here, we're going to kind of drive a little bit more into the calculation side of things. So the first thing we want to talk about is like we talked about the characteristics of data before, and one of the big ones was center. We're always trying to find like the middle of a data set. The first one that you run into is the mean, which we all know how to do. You add up the numbers and divide by the total, how many there are. The upside of this is it's like the ease of calculation. It corresponds to the central limit theorem. So we like that um, you're going to find that there's a certain mean of means that goes on here that always so the mean of the means is the mean of the population, and we'll get into how that plays out when we get a little bit closer to the central limit theorem, but right now just know that the arithmetic mean corresponds to that. The downside of this is that it's like really susceptible to outliers, and this is like fairly easy to demonstrate. So like if I have a data set 1, 2, 3, it's obvious that the mean of this is 2, right? But if I suddenly throw into this, let's say the data set is now 1, 2, 3, 101, I think helps me here, right? So if I add those, I'm going to get, let's see, what is it? That's 2 and 3 is 6. Sorry, 2 and 3 5 is 1 is 6. Let's make it 100. Let's keep it simple. So that's going to give me 6, and 100 is 106, right? I divide that by 4 data points. Right, so 100 divided by 4 is 25. So what is this? This is like 26 and a half, I think. Yeah, I think. 106, 100 divided by 4 is 25. 6 divided by 4 is 1 with 2 left over. Yeah, 26 and a half. So now like my mean jumped way up from 2 to 26 because I introduced an outlier. So that causes it to stretch. So this is what we call a non-robust measure. So that's the term that gets used. That like if something is robust, it will not move when an outlier is added to the set. But here, this definitely causes a problem. So where outliers are common, we prefer to use like the median, and the median is the middle number, or if you have an odd set of, or if you have an even set of numbers, it's the mean of the two numbers in the middle. The huge upside of this is that it becomes more robust. Like here, my set 1, 2, 3. The median was 2. I add the outlier 100 here, and now the median goes from 2 to 2.5, which is a very small change instead of going up to 26 and a half, right? Okay, so it seems like it's not a hard thing to calculate. Yet, in order to find the median, you do have to do ordering. You have to kind of look at the set as an ordered set. And ordering a large set is actually kind of complicated, even when you have a computer involved. It raises what's called the big O number. But so that ordering thing is going to drive the complexity of things. And it's also not in line with the central limit theorem. The central limit theorem crashes around the mean and not around the median. Um, there is actually a way to do median driven calculations. And you will get a variance at a standard deviation that's based on the median residuals. It's not usually commonly used, but it will be used in macroeconomics. part of the reason why economics tends toward medians is that like outliers occur quite frequently. So the median has the advantage of being robust. Um, if you think about like U.S. income, our household income, we definitely don't want to use the mean for that, because there's guys out there like Jeff Bezos, and when you throw Jeff Bezos in the pool, we all look like we're a lot wealthier if we use the mean. Whereas when you throw Jeff Bezos in the pool, um, he doesn't have too much of an effect on our measure of center there. So there you have mean, median. The other one is the mid-range. I know like some people like to say mean, median, mode. Mode is actually more about distribution than it is about center because the mode could be way nowhere near the center. Um, the mid-range though is definitely a measure of center. You take the max, the min, and you take the average of the two. It's really easy to calculate. It's definitely not robust, and it doesn't correspond to the central limit theorem. Um, why do we use it? It can be a good comparison to the mean, to get an idea of how far the data set is askew from the whole. So like if you know where the mid-range is and you know where the mean is, it's going to be able to tell you a little bit about skewness. So it's like the mid-range is where the mean should be if I'm symmetric. But if I'm not symmetric, then the mean is going to be either to the left or to the right of the mid-range. So it's a good way to talk about that skewness. Rounding, when you're using a measure of center, we usually carry one more decimal place than the value. So like if I was to get something like a third, let's say my mean comes out as to like 27 and a third, I would write that as 27.3. If my data set had whole numbers, if my data set had one decimal place, I would make it 27.33. So usually we carry one additional data point or one additional point of decimal point from the data set. So, all right. So let's talk about how to use the TI-84s for this. So let me bring up the calculator. It's fairly simple and straightforward. You get most of this all at the same time. So I'm going to go second plus 712, resets my calculator so I'm clean. I'm going to throw that data set in here. So I'm going to go stat, edit. Okay, so the way to just basically pull this off is I go to stat, calc, and then I run the one variable statistics. I'm doing this on list one. I'm not using a frequency distribution, so I just leave that second one blank. And I hit calculate. And the X bar in the list up here, that's the given mean. So for this data set, I would say that it has a mean of like 17.1. And then if I drive, or sorry, 17.2 by rounding, there we go. And if I drive down, the median shows up here as 15. So you have to scroll down a little bit to get the median. Now there's a whole bunch of other data, and we're going to learn what some of this is. Like if you add up all the points in the data set, you get 464. These are standard deviations. And then you get the 5 number summary down here at the bottom. But the max and the min are there. So like if I had to calculate the mid-range, I would have that available to me as well. All right, so that's like the basic idea of measures of centrality. But like, let's say I've got a frequency table, right? And I want to find some good approximation for the mean. I'm not going to get the mean dead on because I don't have all the data values. So remember, when you summarize, you lose data, but you can get a pretty good approximation from this. What we tend to do is we approximate each class by its midpoint. So we take the values, the two endpoints, we average them, and we get the midpoint of the class, right? So whatever is the midpoint of the class, that's going to be what we're going to use as the values that are represented there. And the calculator handles this kind of nice. So I'm going to clear everything out again and start from scratch. And if I want to put a distribution table in here, I'm going to put in L1, I'm going to put the class midpoints, 15. All right, and then I'm going to put the frequencies in there, right? And now I go stat, and I'm still doing one variable statistic. I'm only measuring one thing here. The values are in list 1. The frequencies are now in list 2. So now I'm going to have list 1 and list 2 in here. So I calculate, and it runs the one variable statistics, and it gives me the mean of this set is approximately 53.2. Now, if you had the actual data values, you would get something that's slightly different from that. But that's, given the data table, that's the best we're going to do. And the median for this data set is 55. All right, so there you have that. One of the ways that this gets used is like calculating a weighted mean, and a common weighted mean is grade point average. So let's say I have this table here, which is my transcript for a semester, right? And I did really well in my writing seminar and kind of okay in calculus. Spanish was okay, it was a B, Philosophy I did pretty good in. Art history, really well in. And these are the credits for those courses. So the first thing you have to do is you have to convert those grades into numeric values. So the typical way of doing that is to make an A a 4, a B a 3, a C a 2, and that's what we've done here. So we load this up as though it's just like a frequency distribution. So I'm going to go in here, I'm going to clear out both of these lists. Remember, when you're clearing out lists, use clear and not delete. If you use delete, the list goes away, and then you have to go and reset those lists and go find them. So always use clear and not delete. So my grades here were a 4, a 2, a 3, a 3, and a 4. But the credits were different for these classes. English was a 3-credit class. Calculus was a 4-credit class. Spanish was 4. Philosophy was 3, and art history was 3. Now, generally speaking, you might want to do some dive as to understanding that it's like you're adding 3 4s to count for the English class, and you're adding 4 2s to account for the calculus class. And you can kind of parse that out a bit. But again, we go stat calc, the one variable statistics, L1 and L2. And my mean there is 3.12, which would be my GPA. Now, please note that this is not how the independent private schools in Baltimore actually calculate their GPA. Theirs is this much weirder system. But most schools, public schools, universities and whatnot, do calculate their GPAs using this standard method. All right, so that's measures of center. Let's get into measures of variation. The easiest measure of variation is actually the range, right? That is, how far is it from the maximum to the minimum value? So you take the max value, subtract the minimum. It's a simple calculation. It is it's very intuitive to understand. It's very, very easily influenced by outliers. It's not very robust. It doesn't also give you a sense of like the local spread of things. So the improvement on this is to go for what's called variance. And variance is one of these things where like we use it but we don't. But we use it as a stepping stone to get to something that's maybe a little bit better. So in variance, we do is we create what's called a residual. So residual is just like how far am I from the mean. So if I have my set and I have a mean value, so let's just say that the mean of my population is 4, right? And I have a data set where, well, I had to create something that would have a mean of 4, right? So 1, 2, 4, let's see, 6, 7, I think has a mean of 4. Let's say that's 13, 17, 18, 19, 20 divided by 5, the mean is 4, right? Okay, so this thing has a mean of 4. So my residuals here are how far each of these are from the 4. So usually we would say that the residual is negative if the number is below this and positive if the number is above this. So the residual for 1 is 1 minus 4 or negative 3. The residual for 6 would be 6 minus 4, which is 2. Okay, but what we do is we get rid of, we don't want that negativity. And so a logical first move here would be like to take an absolute value. Okay, and the reason why we don't use the absolute value is that for calculation purposes, it gets crazy because the absolute value, when you start doing any analysis, becomes, what do you call it, non-differentiable. And that creates all sorts of problems for maximizing and minimizing. So we use, rather than we make the positive using the absolute value, we create the positive by using the squares. So what we're going to do to get the variance is we're going to take the squares of the residual. So we're going to take the square of this, which would be 9. We're going to take the square of this, which would be 4. And we're going to get all the residuals and we're going to add them all up. So we're going to take the sum of the value minus the mean of the population. And then we're going to divide that squared. And we're going to divide that by the number of values in the population. And this is what's going to be the variance of my population. Now, that's okay. Okay. The problem with it is because we squared all the residuals, we're no longer in the unit of the data set. We're in the square of the unit of the data set. So at some point there's like, we're getting a good measure of variation here, but it's not in the right scale. So that's why we are reluctant to use the variance when we're talking about variation. Now, here's the tricky bit, is the sample variance. So when you do the sample variance, instead of taking the residuals against the sample mean and squaring it and dividing it by the number in the sample, you do it with 1 less. And that's like, oh my gosh, why are they doing this? Why did they just make this harder than it needed to be? And here's the reason why. This is one of these things where like you can spend a lot of time trying to figure this out, but it's really not that complicated. So imagine like I have some data points here. Okay. And the mean of that data is probably going to be around here somewhere. So this would be where the mean of the population is. Okay. So here's what's going on here. If I take a sample, right, and no matter where I take this sample, it's going to, let's say I get a sample and I get this number and this number and that number, right? And it's possible that that could happen. The mean of the sample is like way over here, nowhere near the mean of the population. And you're going to notice that the residuals from the mean of the population are like way big, right? But the residuals from the sample are much smaller. So this means that if I took, this is x1, x2, x3, x1 minus mean squared plus x2 minus mean squared plus x3 minus mean squared is always going to be, sorry, wrong way there, greater than or equal to x1 minus x bar squared, the sample mean, x2 minus x bar squared, x3 minus x bar squared. So this sum, the one using the sample mean, is always going to be an underestimate of the variance for the population. So if the variance for the population is some sum over n, and I want this sample mean to be some sum over something, and I want these things to be relatively close, this actually has to be smaller. If I make the denominator smaller for an underestimate, it's going to get me closer to the actual value. Now, I'm going to have to leave it there. The rationale as to why the denominator has to be smaller is in place here. The rationale as to why it is n minus 1, that's like a lot of graduate level math. And you could like actually like do a simulation and try this all out. And what you'll find is that if you do this over and over again and you make the sample larger and larger and larger, it's going to converge to this when I'm n minus 1. And if I make it n minus 2, it's actually going to cause this to no longer be an underestimation, but it's going to cause it then to be an overestimation. So what we found mathematically, and it's kind of cool, is that the n minus 1 is sufficient. So this is why that variance actually has an n minus 1 there. Now that's a deeper dive than like most kids can grasp, but some of your kids are going to get that if you kind of draw out the pictures. This is one of these things that oftentimes in a stats course, like as an undergrad, it gets hand waved at, but I think there's some worthwhile having a conversation about why that n minus 1 is there. But even here, I'm hand waving a bit as to why it doesn't go to like n minus 2 or n minus 3. The n minus 1 actually does have a sense of convergence there, and you can work that out mathematically. I'm not going to do that here because that's like way past the high school level of math. All right, so as we said before, the issue with the variance is that it's not properly scaled because we're squaring all of the residuals. So what we do is we scale it back to normal size by just taking the square root. And when we take the square root, we call that now the standard deviation. So the standard part here is that we're standard and normal back to the size of the data set. So we don't typically work with a variance as is. We just use it as a way to understand the standard deviation. There is deep in all of this a thing called ANOVA, where you actually do take two samples from and you compare their variances, and if the variances are within a certain threshold, you can assume that the samples were taken from the same population. That's something that like I don't teach in the standard stats course, but it could be something worth looking at down the road, but it is one of the applications of the variance. All right, so you have a population standard deviation, right, that's based off the population mean. You have a sample standard deviation that's based off of the sample mean. Never does anybody actually calculate these things by hand. I mean, you could work it out. And, in an undergraduate stats course, they sometimes do spend some serious time having kids do that. But realistically, that's like getting way too far into the woods, or the weeds rather. And it misses the main point. That once you have this thing, it's useful, but spending time calculating it is not really standard practice. So let's talk about how you actually do this calculation. I'm going to put that data set back in that we used earlier. So this is this 1, 2, 3. Okay, I think I have that in there right. So again, you're still going to just use the one variable statistics. Note, I'm leaving that frequency list blank again. And when I calculate it, it gives me both that 13.55, which is the sample standard deviation, and the 13.30, which is the one for the population. And remember that in the sample, we're assuming that we don't have all the points. In the population, we assume that we do, right? And remember that like the population one would be much larger if we had all the points from the samples. So the sample standard deviation from the set is always going to be larger than the population one. You might want to sit with that for a minute to understand why the sample one being an underestimate is going to make it larger if it's pretending like the population has everything. So that's the sample one's always going to be bigger. All right, so that's standard deviation at its root level. This brings us to what we refer to as the range rule of thumb. Okay, range rule of thumb basically says that if I have the ordinary values of the population, that if this is the mean, right, from the thing, I should expect that the range of the population should be between the mean minus 2 times the standard deviation and the mean plus 2 times the standard deviation. Now, this is what the range rule of thumb says, that basically that the range is 4 standard deviations and it's centered at the mean. Does it always work out? No. And do the populations have unusual values? They do. Okay, so like in our example here, if I took this fascinating. Let's take a moment and see what's going on here. Okay, I just did a little bit of an edit in the notes. I'll fix the ones on the thing. You'll never see it there. But if you watch the video carefully, these numbers have changed a bit because there was a miscalculation in the notes, which is now fixed. All right, so anyway, back to the range rule of thumb here. So the ordinary values are going to be between the mean minus 2 times the standard deviation and mean plus 2 times the standard deviation. In our example here, our mean is like 17.2. The standard deviation is 13.30. So we would expect the ordinary values to be between 17.2 minus 13.30. 2 times that, right? 2 times 13.30. times, there we go. That's better. So the lower end of the values we would expect to be negative 9.4, which given all of our values are positive, like, yeah, that's way down there. And if we do 17.2 plus 2 times this 13.30, the upper end becomes 43.8. Now, that's where this becomes like a rule of thumb, because this data set is somewhat skewed. We do get that we have 43.8 here as what should be a usual upper bound. So that means that that data point that's in the set, that's 46, I think, is in the set. If we go back into the notes, there's a 46 in the data set there. That is an unusual value. It's not necessarily an outlier. Outliers are like extremely far away, but somebody in this population that has a value of 46 breaks the range rule of thumb and is what we would refer to as an unusual value. So anything that's more than 2 standard deviations from the mean is what we call unusual. Now, part of the trick here is that the students have to get accustomed to 2 different words: unusual versus unexpected. Unusual means that it's more than 2 standard deviations from the mean or the norm. Unexpected means that some event has less than a 5% chance of occurring. These are not the same thing, and it often confuses students. One of them is about a measure of deviation from normalcy. The other one is about probabilistic modeling, and that something is unlikely or unexpected to occur. So unexpected, unlikely, those are interchangeable. Unusual means that you're in a place where you're far from the middle. All right, so the other thing that comes up here at this point is what we call the empirical rule. If I have a bell-shaped and symmetric curve, normally we would say this is like a normal curve or a t-distribution, something that's bell-shaped. What we get is that 68% of the values in a bell-shaped normal curve are within 1 standard deviation of the mean. 95% of the values would be in 2 standard deviations of the mean, and 99.7% of the values are within 3 standard deviations of the mean. The classic example to use for this is IQ. The standard IQ tests are built so that the population mean for humans is at 100 with a standard deviation of 15 units. So if you kind of play this out, the mean IQ for the human population is 100. If I get out 1 standard deviation, that's going to be between 85 and 115. If I get out 2 standard deviations, I'm now between 70 and 130. And if I get out 3 standard deviations, I'm at 55 and 145. Okay, so here's what's happening. The people that have a range between 85 and 15 is actually 68% of our population is going to be between here and here. So that 100 and that 15 makes that 1 standard deviation from the norm. People who have an IQ between 70 and 130 account for 95% of the population. People who have an IQ between 55 and 145 account for 99.7% of the population. And that'll hold pretty fast. So we use these markers as important things. Like usually we use the 70 here. because anybody who's more than 2 standard deviations below the norm is considered unusual. So we consider that 70 to be the point where somebody who is being tested to see whether or not they could stand trial for like a capital offense or something like that. Usually we use 70 as the break for that. Folks around, that 130, 145 is usually where we get into this idea of people being either gifted or genius, something like this. An important note to make is that the second standard deviation in these curves is also a point of inflection. So what's happening here is if you look at the curve between those 2 points, it's concave down for all you calculus folks. So that's, you have a certain sense of acceleration that's happening here. Outside the 2 standard deviations, the curve is concave up. So that's something that you can also kind of make a pass toward calculus here with the empirical rule. Folks that are doing a psychology course spend a lot of time on this empirical rule. Like you can bounce this off of things like IQ, you can bounce this off of things like height and weight, because they're all bell-shaped and symmetric realities. But you have to have that shape to things. This brings us to the idea of a z-score. So z-score is a measure of like how weird you are on a standard scale, right? So let's say that I have an IQ of 127 and I want to know like how weird am I? Well, what happens here is my z-score says take my value, subtract the mean value, which would be the 100, and divide by the standard deviation of 15. So this is going to become 27 over 15, right? Oops, don't do that. And 27 divided by 15 gives me 1.8, which means that if I had an IQ of 127, my IQ would be 1.8 standard deviations above the norm. That's my z-score. So positive z-scores are above the mean, negative z-scores are below, but the unit here is standard deviations. So this is where standard deviation becomes a unit of weirdness. The larger the absolute value of my z-score, the more weird I am. If the absolute value of my z-score is above 2, I am unusual. So z-scores are a way to do some comparative work, which brings us to the next idea, which are what are called measures of relative position. All right, so we've gotten measures of center, measures of variation. Measures of relative position are like where are numbers as they're relating to each other, where do data points relate to each other. A lot of times when we're dealing with relative position, we build fences. So the first and easiest way that we do this is by using quartiles. So you take like your data set and you drop in 3 fences, Q1, Q2, which is also called the median, and Q3. So between each of these fences are 25% of the data points. So 25% of the values lie there, right? So the center 50% of the data lies between Q1 and Q3. Usually this is like used by a lot of places like colleges and universities, because this is when, or even Garrison Forest on our outward facing documents, what we'll talk about is like what is the center 50% scores of like SAT composites that were accepted. They don't want to tell you who the highest score was or who the lowest score was, but they want to tell you where the bubble in the middle is. So this is what we're coming at here. If you add in two more numbers in this, a minimum and a maximum, so the lowest possible data point and the highest possible data point, that list is what's called a 5-number summary. And that will give you a pretty good idea of how the data set kind of lays itself out in the relative positioning that you're in. Like, are you between the first and second quartile? Are you above the third quartile? Where are you in relative position to the other points of data? The 5-number summary is pretty easy to get on the calculator. It's, again, under those one variable statistics. So let's plug this in here. And you've watched me like throw this data set in here like 5 times now. 2519, there we go. 22, 36 to 34. Oops, 26, 14, 1, 4, 15, 39, 41, 22, 27, 46. Okay, so I think that's all of them. We'll do stat calc one variable statistics. We leave the frequency list blank. And yeah, that's our guy. We scroll down and there's the 5-number summary. So there's your minimum. The first quartile is at 4, so 25% of the data points are between 1 and 4. 25% are between 4 and 15, between 15 and 26, between 26 and 46. Now, this is a small detail, but it's an important one. Q1 and Q3 here are not unique. Oftentimes, there's a lot of different numbers that could stand in for that fence and would still break it into the right 25%. There are not a uniform way of calculating Q1 and Q3. The calculator uses a particular algorithm to determine this. I think it takes medians of medians somehow, but it is possible for two people to break the data set into 4 parts and get a different number. It is not possible for a data point to jump the fence. So the fence can move, but it doesn't move so far that a data point lands on another side of the fence. So there's your 5-number summary. A visualization of this 5-number summary is the box and whisker plot. So let's take this data set and let's show how to do that. If I go second y equals, I'm going to go to number 1 and turn the plot on. My choice for the box and whisker plot is this guy. I'm using L1 with a frequency of 1. Every item in the list is only getting chosen once. The way I get the calculator to correctly format this is I use zoom. Oh, I gotta go back out and then zoom. And I grab number 9 is the stat zoom. When I do that, the calculator figures out where my data is and then windows accordingly. So here's my 5-number summary represented as a data plot. The 2 ends of the max and min, the 3 bars in the rectangle are Q1, Q2, and Q3. If I trace this, there's the minimum at 1, Q1 is at 4, the median is at 15, the Q3 is at 26, and the maximum is out there at 46. So there's your box and whisker plot. That gives you kind of a visual representation of the relative position of the data. So the calculator also deals with these outliers. Okay, so the distance between Q1 and Q3, so Q3 minus Q1 is what's called the interquartile range, the IQR. This is kind of like that middle 50% and how wide that group is, right? We use that IQR to define an outlier, okay? So I'm going to kind of draw, whoops, wrong side. I'm going to kind of redraw over here a little bit to get a picture of what technically is an outlier. So again, you have your data set, right? Here it is. You have this Q1, you have this Q2, and you have this Q3, right? And the distance from here to here is the IQR. Now, you have a minimum down here, and you have a maximum up here. All right, so what I want to do here, and I'm going to cheat a little by using a little bit of magic, but all right, so what I'm going to do here is I'm going to multiply that IQR by 1.5, okay? And then I'm going to check. And if I go 1.5 times the IQR below Q1, so that's going to be like out here. Whoops, don't do that. There we go. That's going to be like out here somewhere, right? So this is like Q1 minus 1.5 times the IQR. Now note, the minimum is before there, so there's no like, there's no outlier on this side. But let's say I hit it over here where I'm Q3 plus 1.5 times the IQR. Anything that's in here would be an outlier. Okay, so it's like so far out, it's more than 1.5 times the IQR above either Q1 or above Q3 or below Q1. So those are like the outer fences. And if I go to points that are above those outer fences, that's where I start identifying things as outliers. Now, what I'm going to do here is to kind of show you something that the calculator can do. I'm going to go in to that data set that I've been working with, and I'm just going to drop one more value in at the end. I'm going to drop in a 100, right? Now, if I did the standard box plot with that, so that would just be hit zoom 9, you see like, okay, that point, the max just went way out there, right? Because that's where the 100 is, right? So if I trace this, remember, things are robust here. I'm still my Q1 became 4.5. My median hasn't moved a lot. Q3 hasn't moved a lot, but the max moved way out there. The bubble doesn't move, but the max moves. So I want to visualize the outlier as separate from the whole. So I want to make the max the highest number that's not an outlier. And that's where this second box plot comes in. So I use this, there's a box plot here. And it's going to say, okay, what do I want to use as the marks for the outliers? And I can use a box or a plus or a period. Let's use the box. It's easiest to see. And now I hit zoom 9. And see, there it is. This point out here, the 100 all by itself is the outlier hanging out there. And the other 5 data, or the 5 number summary shores back up to where it was before. Like if I trace, I'm back to the 1. Now it's still a little bit off that moved the fences because of the calculations, but the data points, you see clearly that that thing is not like in the main population of the set. So this is what's called a modified box plot. And it just gives us another visualization of like, okay, so this thing's stretching, but the main part of the population is here, and this one's somehow a little bit weird, and I have to contend with that in a different way. All right, so that's your modified box plot. Okay, so other ways to do this fencing. You don't only have to have 4 fences. You can actually have more than that. hold on. So like with quartiles, you have 4 fences. When we do percentiles, it's the exact same logic, but now when we break out the data set, we don't have 4 fences or 3 fences making it into 4 pieces. We have 99 fences making it into 100 pieces, right? Where each piece is 1% of the population. And these are what we call percentiles. So if I go across here, I would now have like P1, P2, P3, and I would break this out until like I get to P97, P98, P99, right? So you now have 99 percentiles. And my data falls somewhere in here. I can fall below the first percentile. I can be above the 99th. Usually I talk about myself being above whatever percentile I'm falling in. So to figure out what percentile my data point is above, what I do is I say, okay, P, I count how many data points are below me. That's P. That's B rather. Take the total number of data points and multiply that by 100, and I round down. So this is always a rounding down to the nearest integer, and that will give me the percentile that I'm above, right? So like if I did this calculation and I got, let's say, 37.2, this means I'm above the 37th percentile. If I get something like 0.46, I want to say that I'm below the first percentile. You can be above the 99th. There is no 100th percentile. Above the 99th is as good as you get, right? So it works the same way as quartiles, but only there's 99 of them instead of 3. Another one that comes up, it's like when you're doing admissions work, this comes up, is stay nines. Because like map testing breaks things into stay nines and things like that. Stay nines basically do this. They're related to z-scores. Okay. So you have to remember that like the mean has a z-score of 0, right? So then they start breaking this out. They break it out at a quarter and negative a quarter, right? And then it's by 0.5. So 0.75, 0.1 or 1.25, 1.75, right? And then we go negative 0.75, negative 1.25, negative 1.75, and these are z-scores, right? So we're using with something that's probably bell-shaped and symmetric. The middle one, the middle 50% is one group, and then there's 2, 3, 4, 5, 6, 7, and then there's like 2 eternity out here into 2 eternity up here, and we number them. 1, 2, 3, 4, 5, 6, 7, 8, 9, and these are the standard nines, the stay nines, right? So knowing which stay nine a student's score falls into is a measure of relative position. We make 9 buckets and it tells us where they are. Another thing that happens is it looks like stay nines, but they're not the same. You take the data set and instead of breaking it into 99 pieces or what do you call it? 4 pieces or 3 fences and 4 pieces. You use 9 fences, 1, 2, 3, 4, 5, 6, 7, 8, 9, and this would be D1, D2, D3, D4, D5, D6, D7, D8, D9. And remember, this is equal parts in between these. These are what are called the deciles, right? So they're equal parts in between them. So this would be 10% of the whole in each of these places. That's not going to be true in stay9s, because remember, in stay9s, the stay9s that are in the middle are going to be much larger than the stay9s on the outside, because these are based on z-scores. Or deciles, it has to be 10% between them. You're using 9 dividers instead of 3 or 99. All right, so I believe at this point I'm at like 55 or so minutes. We've covered measures of center, right, which is the mean, the median, the mid-range. We've talked about measures of variation, which is your range, your variance, your standard deviation, and that got us into like the range rule of thumb, the empirical rule, and z-scores. And then we're dropping into measures of relative position, which gives me things like quartiles, percentiles, stay9s, and deciles. In the end, if you start putting these things together, you can start fleshing out like what the distribution or the shape of the data looks like. You get a sense of outliers from the IQRs, right, from the interquartile ranges. So that gives us that other characteristic of data. At times is times. And if you take something over a time series, you get times. So we've gotten into a little bit of the rigor of how do you like talk about numerically these measure characteristics of data. So at this point, we're kind of stopping descriptive statistics, right? So you've gotten like the basic ideas of statistics, right, and how descriptive statistics works. We've gotten numeric or physical representations of things, different types of graphs and models and things like that. We've gotten into kind of ways to do calculations on center and variation and relative position to be able to get some more description in a more kind of technical kind of way. And then we pause and we make a jump at this point into probability. So the next couple of pieces are going to be on probability and conditional probability and Bayesian stuff, which is ultimately going to get us into hypothesis testing and inferential statistics. So one more to go before we get to the synchronous pieces, but hopefully this is helping. All right, so email questions or bring them to the synchronous meeting, and we'll go from there. Thank you.